Hello, this is Bob. This is May 23rd, 2012, and I want to do a demonstration showing dielectric stress. And for that purpose, I have put together a capacitor using a fluid or a liquid as the dielectric. Now what we have here, this is just vegetable oil. I dyed it so hopefully the camera would pick up the action better. And what we have here, one plate of the capacitor is just this cone. That's with a plate in the inside of the cone. You have a plate and the outer edge which extend beyond the plate, and it just dangles. It just sits on the cap. I made this little bracket to hold it. It's electric, it's all aluminum or copper, and I shaped it so I could adjust the height of it, so I could get it to just swing above the dielectric. Now I'm going to set that in the jar. Now the dielectrics are not good conductors at all, and because of that, when electric charge is applied to them through the plates, they shift. The molecules and at the atomic and molecular level, they don't, in their range, they won't pass, they won't conduct any electricity, but they do what they call dielectric stress. And this does not build up uniformly as you might think. This is what the demonstration. And the other thing, now the bottom plate, I just took a jar, the bottom of the jar, I lined it with aluminum foil, and you can see I have a clip on here that goes back, because I'm going to be using both sides charges of the Wimshurst, a positive and a negative. Now you could go to ground if you just have one power source, but I've got two and I'm going to use them. And in that system I'm running it, well, you can't see it because I'm going to keep the reason I pulled in so tight on this is because I really want you to see what happens when you are charging up a capacitor. Now, a capacitor doesn't charge up as you might think. The charges go in and it stresses them, but it does not. There is a positive and negative to it, and I'm going to show exactly what I'm talking about. Now here we go. See this? See how turbulent the fluid is? Now that fluid is taking a charge, but there are negative and positive regions in the fluid as it's stressing, and it is actually causing, you can see the cone is oscillating because there are regions of positive and negative. Now you keep charging this, and it'll eventually settle down, is what you're going to see. Then as you can see, it's oscillating more and more. It'll never actually stop. Alright, that's a pretty good charge. Now what I'm going to do is I'm going to you won't be able to see this, but I'm going to short it out. Actually, it's what they call a short. But I'm going to connect the negative and the positive together on each side. You can hear the spark. See the violent action and the turbulence in the fluid. That shows you that it's definitely going the other way. But it's not a smooth transition. A gentleman clear back in the 18th century by the name of Lord Kelvin discovered that even though capacitors, when they're charged, they discharge very rapidly, they pulse. A very high frequency pulse. And now I've slowed this way down. This is the same thing. It processes. In fact, it was very rapid when I first did it. You noticed how turbulent the fluid was, but now you can see that it's slowed down. Now there's still plenty of charge in there. I can flash a fluorescent lamp with it every time it discharges, and it'll do that for quite a while. But as you can see, even in the surface of the fluid, some of it is pulled toward the cone edge and some of it is repelled. You can see the depressions. Well, that's because when it's repelling, they're like charges, and when they're attracting to the cone, they're opposite charges. And this is a process that as it discharges, this will continue. And it keeps going. Now, because of this discovery of Lord Kelvin's, when he published his findings on how capacitors discharge and charge, that it's just not a steady stream of electrical current, it pulses. It actually goes and stops, reverses and goes, and it does this very fast. I've slowed it way up. You can actually see this happening. And when that happens, that's when it'll build up, and that's when it'll flash the fluorescent light. I'm not going to show you that because it's daylight and it just isn't a real bright flash, but the effect is there. But as you can see, there's different regions here of depression, and on this, you're not going to see it, but it happens on both sides all around, and in some cases it's actually pulling the fluid toward the edge of the cone. Well, it is this rapid pulse, high frequency pulse, that the capacitors that occurs when the capacitors are charged and discharged, that Nikola Tesla, when he read about this and found this out, this is what helped him. It was this action that was discovered by Lord Kelvin that enabled him to build his Tesla coil. He needed that high frequency so he could work it with made this circuit using a coil. He called it a tank circuit. But just for you, unless you study that and get into that more. But that's just how it works. Now I'm going to charge it up again. I'm going to do this. You can see that it is not a uniform, very turbulent, and you can see it in the fluid. Here we go. There it goes. You see how it is just really moving all around. You can see depressions and you can see high spots. High spots are attraction, the depressions are repulsion. And there are different zones in it. And like I said, the more as long as I crank the Wimhurst, I'm using Wimhurst is putting out 70,000 volts. And that's what it's absorbing. literally, this is dielectric stress because it's not conducting. Otherwise, there would be a spark between the two plates, and the fluid is preventing that. But it is absorbing all this energy in the form of stress. And they're busy in there, as you can see by the turbulence in the fluid. As you crank more, you notice it finally settles down because it only can hold so much. And then it either dissipates or the dielectric will break down. Well, it's not breaking down, so it's just dissipating. Now I'm going to short it. You see, now I'm made a connection between the two plates. In other words, a short, direct contact. But now we have electrical contact, continuity, and it's conducting going from the top plate, but it is not as steady as you think. Remember, capacitor is considered a electrostatic tool because that's what it holds. When you charge up a capacitor, it's holding static electricity. And you notice before I discharged it and had it disconnect from the windmirrors, nothing happened. It just sat there. But as you can see on this side, you've got fluid touching the upper plate, the cone, and on this side you can see depressions, and it'll do that, and it'll take. Now that I've done this, it'll take over an hour for this to completely discharge all the energy in the fluid. So I just wanted to give you a good show on that and show you dielectric stress and how it was utilized by when it was discovered by Lord Kelvin and utilized and put to work with Tesla in the Tesla coil. Talk to you later. Bye.